Hi, I'm Shahnawaz. In last lecture, we saw that if suppose we have two projective spaces, say Pn and Pm, uh, then we saw their product need not be a projective space. However, we can embed this set, I mean Pn cross Pm, into a larger projective space by defining an injection. So we define an injection sigma from Pn cross Pm into Pn. So this is some larger project n space where this big N is m plus n plus 1 times m plus 1 minus 1. So this map is defined like this. So this sigma takes the uh, tuple of vectors. So here the first component is an element of Pn, so it has to be an n plus 1 vector, and Pm, this is an m plus 1 vector. Say this is b naught up to bm. So it takes this tuple to the vector aibj, where this I goes from 0 to n and j goes from 0 to m. So this sigma is called the Segre embedding. So this sigma is uh, called Segre embedding. And we denote the image of sigma, i.e. sigma of Pn times Pm is denoted by this big sigma. Now, if we set suppose ui to be the set of all elements, I mean all vectors, say ak, where this k goes from 0 to n. So they are all the vectors, all the points in Pn whose ith coordinate is non-zero. Similarly, if uj is a set of all points, say b, k in Pm, while the jth coordinate is non-zero, and uh, similarly we define uij. So this contains the set of all points ai, suppose ak, bl, where this k and l goes from 0 to n and 0 to m respectively, whose ith coordinate is non-zero. Then as usual we have the corresponding map. So we have the map phi from the affine n space to ui. We have the map phi j from affine m space to uj, and finally we have the map phi ij from the affine n space, this capital N, from an to uij. So these maps are defined like this. So as first it is this. So this map takes the point in an, which we denote by say a naught, so on an cap, where this cap uh, means that this term is not there, I mean this term is omitted. So it takes this point to the vector a0 up to an. Similarly, this phi j takes the point say b naught up to bj, where bj is omitted, up to bm, and it maps this point to the vector b0, so on up to bm. And similarly we have the map phi ij from an to uij, which takes the point. So we have the point to say, let us suppose we have the point to say a, um, say 0 0, so on, say aij cap, and so amn. So this is not 0 0 here, this is, yeah, of course this is 0 0. So it takes this point to the vector aij, where I and j runs from 0 to n and 0 to m respectively. Then, as we did earlier, these maps, I mean these phi i's and phi j's, they have the inverses, which we usually denote by psi I. So psi I is a map from ui to an, and psi j is a map from uj to am, and finally we have psi ij, which is a map from uij to an. So now what we do, we define a map. We define a map like this: sigma ij uh, from the affine n plus m space to uij. Now this map is defined like this. So since a and m, n plus m, this is isomorphic to an times am. So a point here, so if we have a point, say a in this affine space, this can be identified as an ordered pair pq, where p is in affine n space and q is in affine m space. So then this sigma ij, it takes the point pq, where p is in affine n space and q is in affine m space, and it maps it to the point sigma times phi I of p, phi j of q. Now one can see that phi I of p takes the point p inside ui, and phi j takes the point q into uj. So this is in ui, this is in uj. So this is some point, phi I of p and comma phi j of q is a point in ui uj, which is in turn a point in pn cross pm. And sigma takes this point, since sigma is a map from pn to pn cross pm to pn. So it takes this point inside pn, since uij is contained in pn. So this map makes sense. Now what we do, we set we have we set this notation here. We set sigma ij of an plus m to be equal to sigma ij. The image of this map is denoted by this sigma ij. Now we have some properties of this Segre embedding here. Let us call this a proposition. So this proposition states that the map sigma from pn cross pm to pn, the Segre embedding is injective. So the map sigma from pn times pm into pn, where n is n plus 1 times m plus 1 minus 1. So this is a map defined as, so this is the first item of the proposition. So this map is defined as, so the sigma takes the point inside pn cross pm, which we denote by this vector ai, where I goes from 0 to n, and bj, j goes from 0 to m. So it takes this point to the vector aij, while I goes from 1 to 0 to n and j goes from 0 to m. So this vector has n plus 1 times n plus 1 coordinates. So we have to prove this is the inject map. So the map defined as this is injective, and the image of sigma, which we denote by the capital sigma, the big sigma, and the image sigma of this little sigma is actually, so this is given as, so actually this is the zero set of, so this is the zero set of the polynomial equations, and let us call this xij xkl minus xil xkj, where I and k they run from 0 to n, and uh, and j and l they run from 0 to m. So this is what we have to prove. And the second item of the proposition is the map sigma ij, which is a map from the affine n plus m space to its image, which is sigma ij. One can note the sigma ij lies inside uij, and uij itself lies in p to the power this capital N, I mean this set here. So this is an isomorphism. So recall that an isomorphism is a morphism which is bijective, whose, I mean, and there must exist some other morphism from this set to this set, such that they when we compose these two morphisms, we get the identity morphism. So let us prove first. So first of all, now to prove sigma is injective, we start with, so let sigma of the point say ai and bj, suppose this is equal to sigma of ai prime comma bj prime. So this is true if and only if I mean this is true. Now sigma of ai bj is actually, so this gives, so this gives ai bj, where I and j run from 0 to n and 0 to m respectively. So this is equal to, because this is equal to ai bj. Similarly, this is ai prime, sorry, this is ai prime bj prime. Now one should note that two vectors are equal if and only if they differ by a scalar multiple. So that means there is a non-zero scalar. So mm, this implies there exists some non-zero scalar, say lambda in k minus 0. Let us call this non-zero scalar, some non-zero scalar lambda, such that uh, this lambda ai, I mean this ai prime bj prime is actually lambda times aibj. So first of all, one should note that these two, this factor and this factor, they are non-zero vectors. So at least one coordinate has to be non-zero. Similarly, this factor and this factor, they are again non-zero vectors. So both the vectors have at least one coordinate non-zero. So this implies there is some coordinate here which is non-zero, and as well as a coordinate here which is non-zero. Now what we are going to do, we are going to choose some, say, so choose, say, I sub k and j sub k, such that, so with ai k bj k. So this is ai subscript k bj k non-zero. I mean, this ik and jk, they lie between 0 to n and 0 to m respectively. So then, so if this is the case, then aik prime times bjk prime, this is also non-zero. So in particular, bjk prime is non-zero. So in particular, bjk prime is non-zero. So therefore, we can divide throughout this equation here by bjk prime. So therefore, we have, so we get, so ai prime is actually equal um, so one should note here, this is true for all I and j. So this would imply ai prime will be equal to lambda times, now we are going to divide by this bj prime. So we have bj here, let us divide this by bj prime times, uh, I mean, this is, so if we substitute j to be equal to j prime, so then we have, for j equal to jk, I mean, we have this ai prime. So for j we have to put j sub k prime. So we are going to divide this through by bjk prime throughout. So we get, this is lambda here, this is ai here, this is b j sub k here, and we are dividing by bjk prime. So this is true for all I, because we are fixing j sub k here. So, or ai prime is lambda times um, bjk over bjk prime times ai. Now lambda is scalar, bjk is non-zero coordinate, hence this is also a scalar, so is bjk prime. So this is some scalar here. So ai prime is some scalar times ai. So this is true for all I. So this gives, so this gives this vector ai prime, sorry, ai sub I is same as a vector ai prime sub I. So similarly, one can prove that. So similarly, one can prove that the vector bj sub I is same as bj sub uh, bj sub bj prime. So in order to prove this is injective, we actually have to prove these two odd pairs are equal, and these two odd pairs will be equal if ai if the vector ai is same as the vector ai prime, and the vector bj is same as the vector bj prime. So this is what we proved here. So this proves the injectivity of sigma. So hence sigma is injective. Now we have to prove the zero set of these polynomial equations is actually sigma. Now to prove this second item, now this is not the second item, this is the second part of the first item. So for that we set, so set w to be equal to the zero set of the polynomial equations xij xkl minus xil xkj. So actually these xi's and xj's, these xij's, they are the coordinates on the space Pn. They are the coordinate functions. So xkj, where this I and k, they run from 0 to n, and uh, j and l, they run from 0 to m. So this is what set w. Now one inclusion is trivial. So if we look at sigma, sigma is of course contained in uh, w. So this is trivial. So to prove this, so let us suppose uh, so let us pick some point in w. Now w is uh, let us pick some point in sigma. Now sigma is the image of this little sigma. So sigma is a map. So this sigma is mapped from Pn cross Pm to Pn. So the image of this sigma is inside Pn, and we denote the image of sigma by this sigma. So this sigma is contained inside Pn. So now we are going to pick some point inside this sigma. So that has to be a vector in m plus 1 times n minus n plus 1 coordinates. So let us pick some point aij, uh, aibj. So this is some point inside sigma. Now note that if we look at this expression, the expression aibj minus aibj akbl minus aibl akbj. Now we have ai here, bj bj, ak, and bl. So this is equal to 0. This is equal to 0. So this means, so this implies, this point, uh, I mean this vector. So this is true for all I and k varying from 0 to n, and j and l varying from 0 to m. So this implies this vector aij, where I and j goes from 1 to n. So this would imply that this is the zero set of the polynomial equations xi yj, sorry, this is xij ykl minus xi uh, xil, and um, okay, let me check this here. Yes, this is xik xkl. So if we set the ij coordinate of this vector inside this, so the ijth coordinate of this vector is aibj. Similarly, the kl coordinate of this vector is akbl, so we get akbl. Similarly, the ilth coordinate is aibl, and the kjth coordinate, since these are coordinate functions, so kjth coordinate of this vector is akbj, which is this expression here. So this turns out to be 0. So this will imply this is a 0 of this polynomial equation. So in other words, that is, which is equal to w. So that is, sigma is trivially contained inside w. Now to prove the other inclusion, what we do, we pick some point inside w, and we end up showing that point is also in this big sigma. So conversely, let let us pick some point, say aij ij, where I goes from 0 to n and j goes from 0 to m. So this is a point inside sigma, sorry, inside w. So if this is the case, uh, uh, we choose some coordinate, say choose k and l, such that the kth coordinate of this vector, which is akl, is non-zero. So if this is non-zero, then we know that the vector aij is same as the vector aij times akl, because um, any two vectors which differ by a scalar multiple are same. So this is ij here, but one should note over here this aij, this lies inside w. So this lies inside w. So that means this aij akl also lies inside w. So if this is the case, then and this is the 0 of this polynomial equation. So that is, so since uh, I mean since aij is inside w, therefore aij, the ijth coordinate of this vector, and the, this is not y here, this is x here. This is my bad, this is x here. So this is the ijth coordinate of this vector aij, and the vector kth lth coordinate minus the ith lth coordinate. and the KSGS coordinate. So this is 0, or the IRGS coordinate and KSLS coordinate is same as the ILS coordinate times the AKL. So this would imply, so this gives, let us call this star, this gives from star, so the vector Aij, this is equal to the vector AIL AKJ, because Aij AKL is same as AIL AKJ. So this is IJ here. But this is same as, so if we look at this point here, sigma of the vector AIL. Now L is fixed here, only I varies. So this is a point in Pn. Similarly, this is the point in Pm. So this is a point in Pn, and this is a point in Pm. So this odd pair is a point in Pn cross Pm. So sigma of this point will lie inside the image of this set, which is sigma ij, sorry, which is sigma. So this is inside the big sigma. The reason for that is uh, the vector, since the vector AIL of I is in Pn and AKJ is inside Pm. So hence uh, sigma is same as W. So this gives sigma is contained in W. So that means sigma and W are precisely the same sets. Now let us prove the second item. Now to prove second item, what we do, we are first going to so we have sigma ij, which is the image of the map, this little sigma ij of a n plus m, while this sigma ij, so this sigma ij is actually a map from a n plus m to uij, as defined as, so this map is defined as, so the sigma ij takes a point inside a n plus m, which we can identify as a point inside a n times am. So this is a point pq, where p is in a n and q is in am. So this is same as sigma of phi I of p phi j of q. So this is what sigma ij. So we have to prove this sigma ij is actually an isomorphism. So I mean, we had to prove, so um, we had to prove. So one should note here this sigma ij from an plus m to uij need not be isomorphism. So if we restrict uij to its image sigma ij, then it may be isomorphism, and we had to prove in that case it is an isomorphism. So we had to prove sigma ij from an plus m to sigma ij, which is the image of this little sigma ij, is an isomorphism. Now to prove this is an isomorphism, it suffices to prove it is a morphism, and its inverse is a morphism as well. So now to prove sigma ij is a morphism, it suffices to prove the result for the case when I is same as j is same as 0. So we can assume that this little I is same as little j is same as 0. So then this sigma 0 0, this is actually this takes a point in an plus m, which is uh, I mean a point with n plus m coordinates, say a1 up to an, b1 up to bm. So it takes this point to sigma of phi of p. Now phi of p is the tuple a1 up to an. So this is now this is not phi, this is phi 0, because I is 0. So phi 0 of a1 up to an, comma phi 0 of b1 up to bm. So this is our sigma, and this is same as no, sigma phi 0 of a1 up to n. This takes this n tuple into pn with first coordinate 1. So this gives 1 a1 up to an, comma 1 b1 up to bm. So now this sigma takes this point, I mean this takes this point. So what we do, we have to take the product of these 2 points. So this will give us a vector in m plus 1 times n plus 1 coordinates, I mean m plus 1 times n plus 1 minus 1 coordinates, because the product of 1 and 1 gives 1. So this gives us the vector Cij, where I goes from 0 to m, j goes from 0 to n. Sorry, this is n here, this is m here. Now what is over c00? C00 is over 1, because 1 times 1 is 1. And for so this is where c00 is 1, and for I and j bigger than 0, ci0 ci0 is ai, cj0j is bj, and cij, this is aibj. So now um, if we look at this map, so if we look at this map the way we have defined sigma 0 0, so the coordinates in I mean this the coordinates in the vector ij are just the product of coordinates inside this and this. So this is a morphism, since the coordinates of the map are regular functions. So this is clearly uh, a morphism. Now why this is a morphism? Because if we look at 1, this is a regular function. If we look at ci0, which is ai, which are the restrictions of the coordinate functions xi, xj, and xij. So this xi will give us ai, this xj will give us bj, and xij will give us xj. So now since these coordinate functions are regular functions, so this morphism, this map is actually a morphism. So this is clearly a morphism, since the coordinates of the map are regular functions. So we know a function is regular if and only if it is given by if and only if it is given by polynomial functions. Now these coordinate functions, they are of course polynomial functions and hence regular. So this gives us, I mean, the, this proves that the morphism sigma ij, I mean the map sigma ij is a morphism. Now to prove it is an isomorphism, we have to exhibit its inverse, and we have to prove that is a morphism as well. Now for that, what we do, we just write the coordinates on these coordinate functions of this big space Pn. So let us define the coordinate functions of Pn by zij. So let zij, where this I is from 0 to varies from 0 to n and j varies from 0 to m, be coordinates on be coordinates I mean coordinate functions on this big space. Then the map is clearly a morphism. So then uh, the morphism, so this is given, so this is clearly a morphism, I mean the map which we are going to define right now. So let us define this by z10 by z00 up to zn0 by z00. Similarly, z01 by z00 up to z0m by z00. Now this is a morphism because each of its coordinate is a regular rational function and hence a regular. So this is the map from z sigma ij to an plus m. So this is a morphism, and of course this is the inverse of the map sigma 0 0. So this is, and this is the inverse of the map sigma 0 0. Hence this is, hence the map sigma 0 0 is an isomorphism. So this is an isomorphism. So that means for any ij, sigma ij is always an isomorphism. So this proves the claim.